Hi everyone, welcome to my YouTube channel Lead Art Sci. In today's video, I'm going to talk about Andersen Thermostat. So let's move on. My name is Zainab Khodi. I have PhD in quantum optics. I did this project when I was PhD student and as a topic in molecular dynamics. So in this video, first of all, I will introduce the different ensemble that I want to talk about and the system that we are interested in studying, and what is molecular dynamics at constant temperature, and how many thermostat do we have, and I will specifically focus on Andersen thermostat. And at the end, conclusion and some references that I had used for this preview actually. Okay, so we have different ensemble: microcanonical ensemble, canonical ensemble, grand canonical, thermal, isobaric, and isoenthalpic and isobaric ensemble. But what does it mean? In microcanonical ensemble, some variables like the number of the atoms or the molecules that you're studying in your system, which is shown by n, and also the volume of your system. For example, if you have so many or a bunch of atoms or molecules which are in interaction and collision in a special volume like a box, so the volume in microcanonical and the number of these particles and also the energy of the system should be conserved or should be constant. But in canonical ensemble, actually, the number of these atoms and the volume and the temperature should be conserved. And as you can see in grand canonical, the chemical potential and the volume and temperature should be conserved. And in isothermal or isobaric, so the N, P, and T should be constant, and so on. So when we are talking about the ensemble, it means we have a configuration of different atoms or molecules which are in interaction with each other. Okay, so consider your system like this: a fluid with a lot of water molecules, or you can consider every fluid. So in this open box, and or not just fluid, even you can consider your system like some molecules which are in interaction with each other, like a gas. So molecular dynamic simulation. Molecular dynamics actually allows for simulating the motion of each particle as a function of time by using equations of motion and functional form of potential energy. So in molecular dynamic simulation, you don't have to use quantum law. So just by using the Newton's law and the equations of motion in this regard, you can actually calculate the force and the potential, and also you can actually simulate by calculating the motion of each particle as a function of time. You can use the equations of motion in this regard, and then you can actually simulate the dynamic of this collision and this interaction between these atoms. That should be the atoms of a gas or a liquid. So by using the molecular dynamics simulation and using the classical physics law, so you can study your system. Okay, so in the previous slide, I've shown my system as some molecule as a fluid in a box, and now you can see, for example, these molecules actually can be like some molecules or atoms in a gas that they are in a box, and you can consider it as a system, and there is some collision and interaction between these molecules and these atoms, and you can just for example, you can consider each atom as a ball, and you can study your system. Okay, and so the system, for example, the fluid of interest is an atoms with coordinates R1, R2, Rn in a cubic volume V with periodic boundary conditions. Each component of each coordinate is a number between 0 and V to 1/3. And using periodic boundary conditions, we imagine that if particle I is at Ri, there is a set of image particle at position Ri plus n V to 1/3, where n is a vector with integer components. The potential energy of the atoms, it is like that. So it means that if you can see your system with different position, and in each position there's a special atom, and if you want to actually define the potential energy of this interaction, you can use this formula that it shows that there is interaction, for example, between the atom in the position I and also the atom in the position, for example, J, and actually you can define your potential energy by using this formula. Okay, so you have to consider periodic boundary conditions. So what does it mean? When you are actually when you're working with a system, you always will be faced with some surface effect, and for getting or to get rid of this surface effect, we have to consider a periodic boundary condition. So what does it mean? It means that you have to consider your system just like that there is no boundary, and it is like this boundary condition is repeating for in a periodic intervals, and it can repeat itself, and so it is you just consider it as an infinite situation. So by considering this, so you are getting rid of the surface problem. So when there is no boundaries, so you don't have this problem anymore. So in molecular dynamics. Another convention that we have to use, it's about minimum image convention. So a particle from central box will interact not only with other particles in this box, but also with their images in neighboring boxes. But you have to consider it is the closest neighbor, the closest image of this neighbor. And when you say it's closest, it means that this distance between this particle in this central box with this image, it should be minimal. Okay, so by considering this condition for your simulation, we will go on. And the equations of motion actually, as you can see here, you can write your Hamiltonian just like this. H equal, so summation pi squared divided by 2 mi. So pi power to 2, actually this is your kinetic energy. And phi or phi is your potential energy. And you also have the Lagrangian equation. So you can see that, so Q is the position, and when you say Qi, it means the position of the ice atom. It means the position of the atom in the ice position. And H is the Hamiltonian, and P actually is the momentum. So the derivative of the momentum with respect to time also is equal to the negative amount of the partial derivative of this Hamiltonian respect to the position. And also you can actually calculate the average force just by using this formula, and V is the velocity. And when you are talking about the ensemble of the atoms, and in this collision and in this interaction, you can define your partition function. And so actually you have a distribution, and in this distribution there is always the exchange of the energy. And this exchange of the energy actually just by doing a little bit mathematics and using the partition function, so you can see that the force actually in your system can be defined like this. And so N is the number of the molecules or atoms that you are dealing with. And so Q, it's the amount of heat actually that can be defined as a partition function. And beta, actually it's 1 divided by kT. So it's just can be defined by Boltzmann constant, and H is the Hamiltonian, and Q it's the position. And when you have n particles, so of course each particle has a position, and so it should be dq to n, and also you have n momentum, so it should be dp to n. Okay, so it is also a good idea to check this formula in some thermodynamic books to make sure that everything is correct. Okay, so but the challenge that we want to actually we want to deal with it, or we want to solve this challenge. So how to perform molecular dynamics at constant temperature. So as I was talking about different ensembles, and in each ensemble sometimes you need to make some variable constant, and then you can study your ensemble and the configuration that you want to actually measure something in. So in this lecture, that is a review for Andersen Thermostat, I'm going to say how we can make a thermostat to make a special constant temperature for your ensemble. Okay, so as you can see here, we need a thermostat. And what is thermostat? So thermostat is a component of a control system which senses the temperature of a system so that the system's temperature is maintained near a desired set point. So what is the root of this name? The name is derived from the Greek words thermos, hot, and status, standing. So there's a reference. I found this in Wikipedia. So in short form, I can say, yeah, by using thermostat, you can make a set point in your system, and actually you can say the temperature of my system is controlled, and I have control to over the temperature to my desired temperature. Okay, this is the meaning of thermostat. And we have different thermostat. Branson thermostat, Andersen thermostat, Nose thermostat, and Nose Hoover thermostat. But in this lecture, actually, I am focusing on Andersen thermostat. So Andersen, his name was Hans Christian Andersen. He was Danish scientist, and so we will see how this thermostat works. Okay, when you have actually a reservoir, so you need a heat reservoir. It means that your system should be in interaction with a special reservoir, and it should be the exchange of the energy between your system and this reservoir. And this reservoir, of course, has a special temperature. Okay, so suppose a heat reservoir at a desired temperature T0 is in contact with the system which has n particles in a volume V. If temperature of the system becomes T0 plus minus delta T, you see that if delta T, it means that the difference of this temperature is positive. It means that the next step in comparison with the first step, so you have increasing, and you have increasing in your temperature, and your system gains energy. And when this delta T actually is not positive, so it means that your system is losing energy. So basically, you can define this change in the temperature of your system just by using this formula. So if temperature of the system becomes T0 plus minus delta T, the system then either loses or gains heat that is proportional to delta T, and heat conductivity is K, and the energy exchange per unit time of the system will be like this. So actually this is about the exchange per unit time of the system. So your system, which is in interaction with a heat reservoir, is exchanging this amount of the energy. So alpha is a dimensionless constant, and K is the conductivity, heat conductivity parameter. And delta T is a difference between temperature, and V to 1/3 actually is the you see this, it's the number of the particles. So each stochastic collisions of particles in the system with a heat reservoir is associated with an energy exchange of -3/2 kb delta T. If the collision rate per unit time and one particle is P, then the energy of the system changes by -3/2 np kb delta T and is related to n by the following equation. So you see that P here is it is like probability that can be written in this form, and I have to check this formula again. Yeah. So let's move on, and I will return back to this formula again. So in other words, the Andersen thermostat couples the system to a heat bath via stochastic forces that modify the kinetic energy of the atoms or molecules. The time between collisions, or the number of collisions in some short time interval, is decided randomly with the following Poisson distribution. So it means when you have this actually molecules, because of the collision and because of the stochastic forces, so each particle has a special frequency, and each particle moves with a special frequency, and you can actually define this set of the frequency by Poissonian distribution, and you can find this information in reference number 1. So nu is the stochastic collision frequency. Okay, yeah, now I have to return back to this formula. Actually, you can make this part equal to actually to this one, and then you can achieve this formula. So nu here is the frequency, and alpha is a dimensionless constant, and K is the heat conductivity, V is the volume, and Kb is the Boltzmann constant, and N is the number of the atoms. And so basically you know the relation between the volume and the density, so we can simply say that density is equal the number of the particles divided by the volume that you have for your system, and then you can actually derive this formula. Okay, so As I told you, alpha is the dimension constant depending on the temperature, distribution, and the shape of the system. And K is the thermal conductivity, V is the volume, and rho is the number density of particles. So if I make it a little bit like, so you can see rho is equal N divided by V. Okay, so let's move on. So new velocities for selected particles are chosen at random from Maxwell-Boltzmann distribution at the desired temperature. All other particles remain unaffected. So basically, this is the Maxwell-Boltzmann distribution, and you can see that it's the exponential distribution, and M is the mass, Kb is the Boltzmann constant, T is the temperature, and you can actually write this this distribution for your system. Okay, so you see that in Andersen thermostat, so you consider a heat reservoir, and this heat reservoir is interaction with your canonical or micro canonical ensemble system, and in this interaction you can achieve to your desired temperature. And this is about Andersen thermostat and how does it work. So there are some advantages and also some disadvantages for this method. So the advantage is achieve the correct canonical ensemble, and disadvantage of this is so the dynamics actually change drastically. So it means that the dynamics of your system changed very, very fast, and sometimes maybe you could not have a good control over your system. So and about the constraint in this method, actually, so the Andersen thermostat should only be used for time-independent properties. So in conclusion, as a result, under certain conditions, the time average of any property of the simulated fluid is equal to the canonical ensemble average of the same property. And so these are some references that I had used to make these slides and to actually talk about this topic. And at the end, I'm happy to say thanks for your attention, and see you in the next video. Bye.